Okay, let's get started. So if you have a homework, I think it's 4 this time. If you have a homework 4 to turn in, it's this first stack right here, which has currently 1 submission in it. And then the other homework pile, which also has 1 submission in it, is from homework 3, if you haven't picked that up. So pick up your homework 3 if you haven't, the one person who hasn't yet. And if you have a homework 4, turn it in there if you're not the one person who's turned it in. Any questions about what we've done so far or anything related to the class, or I guess not related to class either?
How are you doing?
How am I doing? Stressed. I have to get a dissertation done in 2 weeks, and I have like 1 chapter with no results. So that's going to be fun.
Yesterday you said that the people you graded so far have been doing worse than the first time.
Yeah.
Do you have any update on that?
I have no update because I've had no time to actually grade these. Yeah. I will get them to you by either Tuesday or Wednesday next week. I guarantee that for sure. But any other questions? Okay. So what were we talking about last time? What was the big result that we were able to show last time? Yeah, so emptiness for sure, but the first one we showed was that the acceptance problem was undecidable, and then we showed that ETM, the emptiness problem, is undecidable. So that's actually kind of interesting. So this basically tells us that if I give you an arbitrary computer program, there's no way for you to be able to check whether or not that program actually does anything in the general case. For a specific program, it could be easy. You can just look and just simulate it, see what happens. But there's no general procedure because of this to determine whether a program actually does anything at all. Which is actually, yeah.
What do you mean by?
It does anything like, yes. So like returns a value or like prints anything. Whatever you think would reason to be have a non-empty language for a computer program. So it usually means like returns true on some input. So like a Boolean function that returns true on some input. You can't check if a given function can actually return true on anything, where I give you the function and it's an arbitrary function. But if I give you a specific function, you might be able to check, but in general you can't because of this. Okay, so any questions about those 2 results? So how did we prove these? What was the general idea of how we proved them? We'll do more examples, I guarantee you. So the ATM one, what did we do? What was the high-level idea? It was only yesterday. Yeah, right. Right, we had some contradiction with some machine we supposedly could build, but the reason we were able to build that machine, supposedly, was that we supposed that ATM was decidable, and there was some machine that actually did the computation. We supposed that it existed, and so therefore we were able to build a machine based off of that alone that could not possibly exist. Got us the contradiction. Okay, so that's the ATM one. What about the ETM one? What did we do for that one? Well, what we did was we didn't just do a similar type proof with ATM where we assumed that it was decidable, then we built some machine that did some contradiction. What we did was we assumed that ETM was decidable, so that's the same. But the difference is we were able to build a decider for ATM based off our decider for ETM, supposed decider for ETM. And obviously that'll get us a contradiction. So what actually happened there? So for the decider for ETM, so I'm just going to sketch what we actually did. I'm not going to write the whole thing again. So oops, my bad. So I'm trying to make a decider for ATM based off of the decider for ETM. So I'm assuming I can solve the emptiness problem. Then we're using that supposed solution to solve the acceptance problem, which we know to be unsolvable. So, which would contradict the fact that we can solve the emptiness one. So what we did was we constructed a machine that had two behaviors. Let's just do it this way. So it has one behavior which has language of it is equal to everything if M accepts W, and the language of it is empty if M does not accept W. So we did this in a little bit more detail, but that's essentially what we did. We just made a machine. We didn't actually run it or do anything with it other than building it. And it had two behaviors. We built into the source code of the machine to say, if M accepts W by running it inside the machine, then we accept whatever input that we're given. It may or may not be the same as the W string that we're given. So the Turing machine here has input X, which could be completely different from M or W or anything. It's just some input. And we built in the source code to say, if M accepts W, then we just accept this input no matter what. So when we're building this machine, for example, if I run this machine myself, and I run it multiple times, the answer of whether M accepts W is going to be exactly the same every single time. Because I'm not modifying the original machine and the input for it originally. I'm not modifying them. So if M really does accept W, then whatever input this new machine is getting, the one we're making, I'm always going to accept it because the answer is exactly the same. M will always accept W if it really does. If it doesn't, then the answer for that will also always be the same, which means that we'll never accept anything. But notice the two behaviors. The two behaviors have the language either being empty or not. So it doesn't have to be sigma star here. As long as one of them is empty and the other one is not empty, then we're okay. So why are we doing it that way? We then run the decider for ETM on this constructed machine. Because the decider says, I will always tell you the right answer, whether your language is empty or not. That's the purpose of the decider for ETM. So it'll tell us whether or not the language is empty. Well, if the language is empty, then the only way that possibly could have occurred is if the original Turing machine M did not accept W, because that's what we built into the source code to do. But then if the decider says, no, your language is not empty, the only other possibility is that the language is, in this case, everything, which means that M accepts W. So this decider for ETM implicitly can tell us whether or not the original machine accepted the input. And then we can determine what to do after that, whether or not we should accept or reject at the very end. So that's the essential idea. We built this machine that had these two different behaviors that depended on whether M accepted W. Any questions about that? Mm-hmm.
So how is it Why can't we use that to say that ATM must be decidable?
A good question. So why can't we use this to show that ATM is decidable? Well, we proved it wasn't, but even if it was, this doesn't tell us anything because this relies on ETM being decidable. So the only way that this machine could ever work is if ETM is decidable, because step 2 would fail. Well, if it wasn't decidable, step 2 would contradict that fact. Because step 2 runs the decider for ETM, but if there isn't one, then I can't do step 2. That doesn't show that there's no decider for ATM, but this method will not work.
So if we went about proving ETM is undecidable first, would we have gotten something else?
Yeah, so it's considerably harder to prove ETM undecidable directly without using some other result, like ATM in this case, but because the one for ATM, we use the input to the machine to help get us the contradiction, whereas ATM doesn't have that property. It is possible, but and I'm pretty sure it's a lot harder to do, but I'm pretty sure you can do it directly. Yeah. Any other questions? Yeah. So the contradiction here is, well, if ETM were decidable, then we just built a decider for ATM. Could a decider exist for ATM at all? No, because we proved yesterday that it was undecidable, that there's no decider for ATM. So that contradicts the fact that there supposedly exists a decider for ETM. Because if there was one, then we can build one for ATM. But we can't. So that shows that ETM was undecidable. Any questions about the style of argument? So we're going to do two more, at least one more problem, maybe two, and then we'll try to generalize this to a whole class of problems, which will make proving problems like these far easier than this. But we need machinery to get there. So let's do one more. So for the DFA problem, we talked about, after the emptiness problem, we talked about the equivalence problem. So here, if you recall, we have two machines. So in this case, they're both Turing machines, and they have the exact same language. So what do you think we want to determine about this language at this point? What is there? No, about EQTM. What do we want to know about EQTM? Is it decidable or not? How many of you are in the decidable camp? How many of you are in the undecidable camp? Yeah, so in fact it is undecidable. Yeah, pretty much anything about Turing machines is undecidable. Some things are decidable, but very few. And we'll see why in a bit. Okay, so we want to show that EQTM is undecidable. So let's suppose that there exists a decider for it. So try to follow the same method of proof as before. So suppose EQTM is, let's give it a name for the decider, decided by X. Would that work? Yeah, X is fine. I didn't want to put E here because we're going to talk about EQTM and then another language that has E in it, so it'd be kind of confusing. So let's just say that X is the Turing machine that decides EQTM. It takes two machines, not one, two machines, and determines whether or not they have the same language, supposing it exists. Okay, so what do you think we're going to do with this supposed decider based on the proof that we did for ETM? Well, what did we do there? We supposed a decider existed for ETM, then we built a decider for ATM, which we know can't possibly exist. So now we're supposing that there's a decider for EQTM. Now we should probably make a supposed decider for either ETM or ATM, because both of them are undecidable. So if I can show that I can make a decider for one of the two, then I think we're okay, because both are undecidable. So it's kind of a curse at this point when we start building up this library of problems to choose which one to do, because some of them are a lot easier to do than other ones. So in this case, it'll actually be a lot easier if we try to build a decider for ETM, not ATM. So let's try to build a decider for the emptiness problem. So what is a decider for the emptiness problem take as input? Not sure how that happened. What does the emptiness problem take as input? Just a single machine, right? Whereas the EQ problem takes two machines. Okay, so let's just try to get that straight. So we're trying to build a decider for ETM where it takes a single machine as input. It doesn't take two machines or with an input or an input string or whatever. It just takes a single machine and nothing else. So where M is a Turing machine, well, it doesn't really make sense for me to feed this machine that we're given as both of the pieces to the one for EQTM, because any Turing machine is equivalent to itself. So I can't just feed the machine into its in both places for EQTM, because that won't tell us anything about whether it's actually empty. But so for that reason, we should probably make another machine in here that can help us with the emptiness problem. So we have a machine that we're given that could have any language at all, but we're trying to solve whether it has empty language or not. So we should actually make a machine here. But what properties should this Turing machine have? Well, so let's just say we're building this machine right here. Well, let's just say I feed it and the machine that we're given, the M machine, into the decider for EQTM. Well, we kind of want the answer to be, if EQTM says yes, then the original language of M is empty. And if they're not equivalent, then the original language of the machine is not empty. So what should the language of this constructed machine be? You want me to spoil the punchline? We're going to make a machine that has empty language. Just a simple machine that has empty language. And I'm going to call it M sub empty. That's the name of the machine with empty language. And then what we'll do is we'll feed the string M with M sub empty into the supposed decider for the equivalence problem. So I'm going to feed the arbitrary one that we're given and the one that we just manufactured that definitely has empty language. We don't know if the one that we're given has empty language, but we know the one that we have, the one that we made, has empty language. Well, X is a supposed decider. So if X comes back and tells us, yeah, they have the exact same language, the empty language and the one that we're given, what does that tell us about the original machine? It has empty language. Cool. So what should I say for the decider for emptiness in that case? Accept or reject? Well, we just determined what about the machine? It has empty language. What should I say for the emptiness problem? Accept or reject? I got both answers. I didn't get a maybe, which is good. Should I say accept or reject in this case? Accept, right, because we just determined that it's empty. I'm trying to solve the emptiness problem, so I should say accept in that case. So if x accepts, then we accept. If x rejects, then we also reject. Because if x comes back and tells us, no, they're not the same language, then it's not possible for them to have the same different languages, one being empty and the other one also being empty. So that means that the M machine must have non-empty language, which means we reject. Yeah.
Wait, so x just determines if the person is equal to the same?
Yeah. So that's the supposition up here. I'm supposing that x does this. This will actually get us the contradiction, but I'm just supposing it can be done. Yeah. Other questions? So this one's a little easier than the first one because we didn't have to think about the two different behaviors thing. We just made a machine that definitely has empty. Then the two behaviors really are that they have the same language or they don't. And that's essentially what we do here. Any questions about this? How it went? Yeah.
You didn't specify. I mean, the thing that we're trying to prove doesn't have two inputs, like two languages, or two machines that we're trying to prove equality.
Yes, the X machine does. The one for equality. I'm using it to supposedly to build a supposed decider for the emptiness problem, which we know can exist. So I'm using its supposed existence to make a decider for a problem I know can't be solved. And so by that reasoning, then there can't possibly be a decider for the equivalence problem. Because if there were, then I can solve the emptiness one. Other questions? Okay, so for this reason, because ETM, the emptiness problem, is undecidable, then the equivalence problem is also undecidable. Okay? That's actually pretty interesting that it's literally impossible to build any algorithm with as many compute clusters as you want to determine if two arbitrary programs do the same thing. Isn't that weird? Even if they don't look the same, whether or not they do the same thing, you can't check that. There's no algorithm at all. It's not that we're just not clever. There literally is no algorithm to do it. Pretty shocking. Any questions about how we actually did the proof, though? Yeah.
So it's just mostly just the whole point of it is since we're using it for building the ETM, in that sense we can't do that. We also.
Right, yeah. So I'm supposing it exists, then on that supposition alone, I build a supposed decider for a problem I know can't be solved. And so you can think of it like its existence implies this existence, but the contrapositive says if the ETM problem can't be solved, then this problem can't be solved. It's just the contrapositive, which is the same statement logically. And so that's exactly what happens here. Other questions? Do you want to do one more of this type of problem? Yeah, I think that might be useful. What could be interesting? Oh, so here's something that's kind of interesting. What if we wanted to determine, okay, I have this computer program running, or maybe we have a computer program running in a bunch of airlines or something that have a very small footprint, and then there's a Java executable in there, or maybe there's a runtime environment so that the program can actually run on these airlines, but they have a small memory footprint. What if we wanted to determine whether or not we can actually simplify the actual the source code of the actual program to, say, make it a DFA instead of just an arbitrary program? That would actually be kind of nice to be able to say, okay, we can solve the exact same problem back into DFA land where all the properties are nice. That would actually be kind of useful. So let's actually talk about this language. I'm going to call it regular TM. And I actually didn't mention this, but I have absolutely no idea why the languages are in all caps. Maybe they're angry at us. I don't know. It's just convention. I don't know why they're in all caps. But yeah, that's exactly what it is. But this language here is just a set of single Turing machines. So it's not like two with EQTM business. It's the same kind of idea as the emptiness problem. It's single machines. So M is a Turing machine. And instead of the language being empty, here the language is regular. So the language of the machine is regular. So yeah, so instead of just empty, the Turing machines that accept everything are in there. The ones that have just odd length strings are there. Any DFA's language as a Turing machine, they're in here. And what do you think this language is? Decidable or not? Yeah, it's undecidable too. It's kind of a shame, but this whole area is kind of depressing. For reasons that you might expect, but the other reasons are that a lot of problems that we really care about, like this one, where we want to simplify these complex programs into these really simple machines, cannot possibly be done in the general case. Okay, so yeah, so we want to show it's undecidable. So let's suppose then, just like before, that this language, this regular TM thing, is decided, let's call it X again to keep with the theme. So I'm supposing that this machine X can take a machine as input and can determine whether it's the given machine's language is regular or it isn't. We're supposing that can be done. So unlike EQTM though, there's not really such an easy connection with the emptiness problem, because with the EQTM one, we only needed it to be empty or not. Here, we need to pick one language that is regular and one language that isn't regular, because we want these two different behaviors. One to correspond to M accepts W if we're doing ATM, and the other one to correspond if it doesn't accept W. So what is your favorite regular language? The one that is regular in any choice. It doesn't actually matter. What's that? 0. The string 0, 1. Okay. So now I'm going to have to adapt the proof a little bit because I'm used to the other languages. But okay, so let's keep a thought bubble right here. And we want to have one language called L1 to be just the single string 0, 1. I'm guessing that's what you meant. Okay. So we have one language that is regular. Now we need another language that isn't regular. Any choice? Yeah. So the 0 to the n, 1 to the n guy, where n is at least 0. It's actually kind of good because L1's a subset of L2, but it doesn't actually matter for our purposes. Okay, so what we want to do is we want to build that machine again that has two different behaviors. One, it has behavior like L1 if M accepts W, and it has the other behavior if M does not accept W. Okay, great. So let's see. Yeah, okay, so I'm going to have to modify the argument I'm used to. So let's try to decide ATM. To decide ATM. So, a refresher. What does a machine for ATM take as input? What are the things that it takes? A machine and a string W, yeah. So I'm not going to say M is a Turing machine and W is a string again, because it should be clear by now what those two are for. And again, we're going to do this two-sided behavior. We want it to behave like the regular language in one case, and we want it to behave like the non-regular language in the other case. So let's construct a Turing machine. Any good names for a Turing machine? Other than suffering? Y, okay. Y, perfect. So Y is going to take an arbitrary input. Okay, I shouldn't use X. I should use, let's do Z. Another letter. Yeah, one of the weird things about this area is that you run out of names really quickly for things. It's kind of sad. So therefore, we invented the Greek alphabet to extend our alphabet. Not true, obviously, but anyway. So on input Z, so then we're going to do some stuff in here. So we got to figure out what we're doing in here. So here's my pro tip when you do proofs like this. What you should do is, immediately off the bat, you should do one of the two cases immediately. So here, no matter what M does on W, no matter what it does, we're going to behave like one of the languages. And if M accepts W, then we behave like the other one. Okay? So no matter what happens, we're going to behave like one of the two languages here. And if M accepts W, then we behave like the other one. Okay? So therefore, if M accepts W, then we behave like the other one. And if it doesn't, we behave like the one we already are started with. So that's the pro tip on how to actually do this. So how would you approach this one? I mentioned that L1's a subset of L2. What we can do in this case is say, if the input that Y gets is equal to the string 0, 1, just accept it immediately. So if the input Z is equal to 0, 1, we're going to accept it immediately. But then if M accepts W, then we behave like the 0 to the n, 1 to the n1. Okay, does that make sense? Yeah.
Why do we switch when we accept?
Yeah, so the weird thing here is that because of the language choice here, I needed to do the opposite of what we usually would. So we're going to have to flip the answer, I think, at the end. Yeah, so the key here is that if M does not accept W, I will always be like L1. So the language of Y will be L1 if M does not accept W. But if it does accept W, I'll accept all of the other strings that are in L2. And so let's actually complete Y, and then we'll talk about it more. So the second step of Y is run M on W. If M accepts W, then I'm just going to complete it, and then we'll talk about it. Then if Z is of the form 0 to the n, 1 to the n, accept, otherwise reject. And so this is the entire Y machine here. So why are we doing this? Kind of an existential question, right? Why are we doing this in the first place? Okay, anyway. This is kind of philosophy, but it's kind of not in the same vein, but anyway. Let's see what actually happens here. Well, either M accepts W or it doesn't. Any disagreement on that? I hope not. Because it's one of those two. So let's suppose that M does accept W. Okay? So it really does accept W. Does the Y machine still accept the 0, 1 string in step A? If M does accept W, does it accept the string 0, 1? Yeah, because it accepts 0, 1 no matter what happens. Cool. But because M accepts W, doesn't it accept all the other strings that have zeros and the same number of ones afterward? Because that's what step B does. If M does accept W, then the machine Y will always accept strings that are of the form 0 to the n, 1 to the n, because that's what's built into the source code to do. But if it's not of that form 0 to the n, 1 to the n, I'm not going to accept it anyway. So I'm never going to accept any other string at all, regardless of whether M accepts W. So now let's consider, so because M accepts W here, I really do have the language 0 to the n, 1 to the n, because I accept exactly those strings and no other ones. So now let's consider the case that M does not accept W. Do I still accept the string 0, 1 and only that string? Look at step A. Does it matter whether M accepts W in step A? No, it doesn't matter. Well, if M does not accept W, will the Y machine ever accept anything else? Will it ever reach another accept step? No. So in fact, if M does not accept W, then the language of Y is just the string 0, 1. Pretty cool. So in one case, the language is regular, and the other case, it isn't. The regular case is because it's finite, and so therefore it's regular. Well, do we have a supposed check to be able to determine whether a certain machine has a regular language or not? It's on the screen. Yes. What's the name of it? What's the machine that can tell us whether some Turing machine does have regular language or not? We called it X. Okay, great. So let's run X on that machine Y that we just made. So we're running it on the machine that we just made. Because the machine X takes just a single machine as input. And it tells us whether or not the language of it is regular. Well, let's see. If X accepts, and this means Y's language is regular, so if Y's language is regular, did M ever accept W? No, because if it did, then we'll accept all the strings of the form 0 to the n, 1 to the n. But if we did that, what's the language of the machine? Regular or not? Not regular. So therefore, this tells us that M does not accept W. So what should we say for our supposed decider for ATM? If we just determine that M does not accept W, and we're trying to solve the acceptance problem, we should say reject. So in this case, we should say reject. And in the other case, if X rejects, meaning that the language of Y is not regular, then that must mean that M accepts W. So therefore, we should say except here, as you might expect. Yeah, so I think going back to your question, we had to flip the answer here because the way that I usually do this has the construction of the language a lot easier to do, where you have the answer at the very end being exactly the same. You don't flip the answer, but we just had to reason a little bit more. But
So in this particular proof, we needed to use an example of regular language and another one that is not regular language. There's no way for us to do it general, so it works for everything. We have to use an example.
so we're gonna actually get to a more general way of doing these proofs, where you have the behavior of the machine either being having some kind of property that you want, which is regular, and because the supposed decider can tell you whether it's in this language, regular TM, or it isn't, because that's what a decider does. So then we need to have some machine that belongs to regular TM that it behaves like, and then the other case, it behaves like a machine that's not in there. And so the decider then for regular TM is in correspondence with those two possibilities. Because if it happens to behave like one of them, then it can't behave like the other one, so we can make a determination of whether M accepts W at the very end. And then the other, if it behaves like the other one, then the answer is the exact opposite. So in this case, we could have picked any language that is regular and any language that isn't regular. As long as we can build a machine for both of them, then we're okay. So if we actually go back to, actually we can just stay here. I could have picked sigma star and 0 to the n, 1 to the n. I could have picked even length strings and palindromes, because palindromes are not regular. So I could have picked any two examples that I wanted, as long as one of them is regular and one of them isn't. Because if both of them were regular or both of them were not regular, the machine X is going to always say the same answer for either of those two possibilities, and then we can't differentiate between them. And so therefore it won't help us at all to determine whether M accepts W or not, because it won't differentiate between the two possibilities. So that's why we have both of them. Other questions? So let's actually take a break now, because the thing that we're going to get to is kind of substantial, and I want some time for it. So let's take a break.